Hello, good evening, everyone. A warm welcome to all. It's a wonderful day, and I feel privileged to extend my warm welcome to all presented over here. This is a new start bi-weekly webinar series. So, now, without further ado, I am inviting our most respectful Mr. Sabik PV, Chairman of IEEE Malabar Subsection. He is serving as Associate Professor at KMCT College of Engineering for Women and has 17 years of teaching experience. For some briefing and introduction about our webinar, over to you, sir.
Yeah, thank you, Rasmina. Good evening, one and all. Once again, welcome you all to this bi-weekly webinar series. This is actually organized by IEEE Malabar Subsection in association with IEEE Malabar Hub. And this is our second edition. Second edition in the sense means we had earlier weekly webinar series, which started in June 2020 during our lockdown period, where we all were sitting in home ideally. So during that period, we thought of sharing knowledge through these online platform. And with that intention, we started off this webinar series, and it successfully completed 100 episode. And eminent speakers from various industries as well as academics has delivered their talk, which was useful for all students, research scholars, and faculty. So we are expecting this second edition also to be a successful one. And today is the first webinar of this series. And today's series we have supported by IEEE student branch of MEA Engineering College. Thanks for the support given for this webinar. So hope in coming editions we will be associating other SBs as well as to jointly associate with our Malabar subsection. So hope this will be a great event. So all the best for all the participants. So thank you from my side. Okay, thank you.
Thank you, sir. Thank you for briefing. Thank you for joining today for our webinar on the topic Brainwaves Modeling and Decoding, conducted by IEEE Malabar Subsection and IEEE Malabar Hub in collab with IEEE MASBC. So just a while of little housekeeping before we get started. To keep the quality of sound functional during the meeting, please mute throughout the meeting unless it's instructed. If you have any queries during the presentation, please type into the chat box. At last, the feedback form of the webinar will be provided at the end of the section. So please make sure each one filling the form. So now I accordingly invite our speaker of the day, Dr. Dileep Ji. He completed his BTech in Electrical and Electronic Engineering from the Government College Engineering, Idukki, MTech in Power Electronics from NIT Warangal, and PhD from IIT in Solar Photovoltaic Power System. He is the author of Distributed Generation and Smart Grid textbook. His research interests include renewable energy, smart grid, brain-mind studies, consciousness, and meditation, etc. Welcome you, sir. To our esteemed audience, over to you, sir. Sir?
Thank you. Thank you. Can you all hear me?
Yes, you're audible, sir.
Okay. And the screen is also visible, I think so.
Yes, sir. Screen is visible.
Okay. Thank you. So actually, today we'll discuss how to model the brain. So starting from this graph from the fundamental unit and how to decode the brain waves. So brain is simply a network of neurons, and when it is fired, signals will flow through the neurons, and definitely it will produce some waves. And by decoding the wave, we can come to understanding of the working of brain. So first of all, we'll try to understand how to model the brain. So human brain weighs about 1 to 1.5 kilograms. Basically, the weight will be vary from person to person. So there will be slight variation. And it is basically composed of neurons. The fundamental unit of brain is known as the, yes, the fundamental unit of brain is known as the neurons. And recent estimates have suggested that the brain contains something around 86 billion to 100 billion neurons. So the number varies from individual to individual. It is estimated that it will be around 86 to 100 billion neurons in our brain. So it is in this one show. So can you see the pointer? So this is actually a neuron. Neuron is actually fundamental unit of brain. So a neuron has a cell body. You can see here, and the cell body there will be a nucleus, and from the cell body there will be a number of dendrites. You can see here these projections are known as the dendrites. So these dendrites actually receive the information. So that information can be light, sound, taste, such anything. So in the nose there will be smell receptors. In the tongue there will be taste receptors. Okay, some kind of different kind of receptors will be in the different sense organs. So this dendrites actually receives that impulse. So that will be collected to this cell body, and all these, you can see number of dendrites are there. All the impulse will be added up in the cell body. And if the potential is above certain threshold, an action potential will be generated. And that action potential will be propagated along this fiber. You can see here. So this is known as axon. That will be propagated along the axon, and it will reach these terminal buttons. You can see here some button-like structure here at the tip, and it will reach here the terminal button. And this terminal button will be connected to another dendrite. Okay, so you can see same structure like this is here, and it will be conducted from to the nose to the brain. At the end, in the brain, there will not be further synapses where the knob will be connected to another dendrite, because it will be interpreted there in the brain. There is no need of further connection to carry this signal. So this point where the knob is connected to another dendrite is known as the synapse. Okay, so here from this point, all this will be added up and it will be conducted towards this point. So you can see here, all this point, it is conducted electrically. Okay. So this structure is known as myelin sheath. Actually, this myelin sheath is an insulator. So that insulator is connected here because it will help to improve the speed of conduction from this end to this end. So this is actually the fundamental unit of the brain and the operation of the fundamental unit I was explaining here. If you have any doubts, you can ask it now itself. Oh, now, if it is clear, we will cut a piece of this cell body here, a piece of this cell body, and see what all are there, because we are going to model it. So we need to see what is there within a small part of that cell body. So within that small part of the cell body, so we can see here, this is that small part of the cell body which is cut and zoomed in. So within that small part, you can see number of channels are there. These are channels through which ions are moving in and out. So you can see here, some ions are moving out. Here, some ions are moving in. And you can see here, some structure like this. There is a button and there is a tail. There is button and a tail. So this is actually known as the cell membrane. Cell membrane contains a bilipid layer. This bilipid layer, you can see one end is facing outside, one end is facing inside. The tail is facing inside. Okay, the tail is actually water repellent, and this is water loving. The head, the button is water loving. Okay, so it is actually bilipid. It is basically an insulator. It doesn't allow the flow of ions through it. Okay, and these channels, you can see through these channels, ions are moving in and out. So, and these channels will be permeating some ions only. It will not allow all the ions to move in and out. It will be selective. So the channels will be selective and the cell membrane will be completely insulating all the ions. It will not allow ions to flow in and out. So this is outside of the cell. This is inside of the cell. So here you can see this part. This is inside. So inside part is here and this is outside part. Okay. So this blue one is actually N plus channel and green one is K plus channel. And there you can see another stuff here. This is actually an N plus Na plus K plus pump. So Na channel and K channel allows the free flow of ions. When it is open, ions can freely flow. And when it is closed, definitely it will not allow the flow of ions. And this pump, Na plus and K plus pump, actually pumps the ions in and out of the cell. So you can see green one is K plus. So 2 K plus ions will be pumped inside, 3 Na plus ion will be pumped outside with the expense of energy. That is shown here as ATP. So it will spend energy and pump ions inside and outside. So this pump really maintains an equilibrium here within the inside and outside. And these channels will be on open and closed depending upon the impulse. Whenever some impulse comes, some channels will be open, some channel will be closed, so that the ions will flow inside, in and out. So when the ion channels are open, the ions will flow in and out so that the potential will vary. Okay. So when these ion channels are closed, the pump will operate and it will maintain some potential. So that potential is known as the resting potential. Generally, for a neuron, the resting potential will be around minus 70 millivolt. So when there is no impulse, the membrane potential will be at minus 70 millivolt. So whenever a signal comes in, some channels will be open, some channel will be closed. Okay, then these ions will move across the cell membrane. So the potential will vary. Once the potential variation is up to a threshold, an action potential will be generated. So definitely when an impulse comes, an action potential will be generated if that impulse is sufficient to generate a threshold. So definitely that particular impulse will be encoded into this action potential. So action potential is generally an on-off signal. When the impulse is sufficient to generate an action potential will be generated. When the impulse comes to threshold, an action potential will be generated. So the magnitude of an action potential is fixed. That won't vary. But depending upon the intensity of the impulse, number of action potential generated will vary. So depending upon the impulse, number of action potential will be varied. How many numbers? So say the impulse is very small, then definitely there will be 1 or 2 action potential only. The intensity of that particular signal is large. That means large number of action potential will be there. Number of action potential will be more. So the information of that particular impulse will be encoded into the frequency of action potential. And that action potential will be propagated all the way from that particular sense organ to the brain. So if the eyes are that particular organ, the signal will be transmitted all the way from the eyes behind to the occipital lobe. In the occipital lobe, that impulse will be decoded and brain will perceive what it is seeing. So the number of impulses will actually have the information of the object that what we are perceiving. So write down, if it is a mouse, so the light rays will fall on the mouse, then that will be reflected back and it will fall on the retina. in the retina there is rods and cone cells. That is a receptor for light. Then that signals will be received, transmitted from the eyes to the brain through the optic nerve. So in the optic nerve, that action potential will be there. That action potential will be transmitted all the way from the optic nerve to the brain. And the brain will then decode and perceive what it is. So within the brain also, we have large number of neurons, isn't it? So from the optic nerve, it will be transmitted all the way through the brain to the occipital lobe, where that particular signal will be decoded. So definitely, this signal has to travel some distance from this optic nerve or from the retina to brain occipital lobe, isn't it? So some kind of electrical activity will happen within the brain also throughout these neurons. All the neurons will fire and some action potential will be generated. And there are synapses also. And in the synapse, the synaptic potential will be generated. These all are potentials. The sense means electrical activity. So this electrical activity can be recorded outside using an electrode also. That we will discuss at the second part. So initially, we will see how we can model this particular neuron. The sense means how we can model this part. Okay, so let's see, first of all, what all are here. Here there is an insulator. I said this is a bilipid layer. This is an insulator, isn't it? And this is a channel, ion channel. This is sodium channel. This is potassium channel. So based on our electrical knowledge, we need to look into this and we need to model. So you can see here positive. You can see I have written here. Yes. Okay, some noise. So actually you can see here some positive, here some negative. That means this side is positive, this side is negative. So positive and negative separated by an insulator. Can you relate it to something? But you are familiar with electrical domain. Positive charges, negative charges, and it is separated by an insulator. Somebody can turn on a microphone and respond. If you can relate to something. We will come to it later, but I was trying to get a response from the crowd. So have you seen anywhere this stuff? Positive charge and negative charge separated by an insulator. In electrical engineering, something similar is there. Somebody can just predict. Actually, your prediction will be correct. Positive, it is simple. Positive charge and negative charge. Two plates separated by an insulator. See, this is a plate of positive charge. This is another plate of negative charge. And this is insulator. Bilipid layer is insulator. It won't allow ions to flow across it. So have you seen anywhere this kind of stuff? Okay, you just check in your memory. And this is actually an ion channel. Ions are freely flowing across this one. So how to relate this one to an electrical different parameter? So this one you can relate, and this one also we can relate. That we'll see later. You can think. And if you have an answer, you can respond. And those who have an answer can respond. What you can relate. If there is no answer, I will move ahead and we'll come to it later. So active transporters and ion channels that we discussed. So how ion movements produce electric signals? So there are difference in concentrations of specific ions across this cell membrane. And these cell membrane channels are selectively permeable. I said earlier also, this channel that will allow only potassium ions to move across this. And this one will allow sodium ions to move across. So these are selectively permeable also. And across this membrane, there is concentration gradient also. That means inside the cell, potassium ion concentration will be large. Outside the cell, sodium ion concentration will be large. So there is a concentration gradient also. So there is always a tendency for this ion to move across, because potassium ion from the cell, inside part of the cell, will always try to move outside. And the sodium ions which are outside will always try to move inside. Okay, so always ions or any other thing will try to move across the concentration gradient. So this concentration gradient will create a potential, isn't it? So there is potential, means the tendency to move. So in a dam, when we consider a dam, the water is blocked. So the water inside the dam have a tendency to move down because it is in a higher potential. Like this, sodium ion is more outside, and potassium ions are more inside. And these ions have a tendency to move across the cell until the concentration gradient is diminished, or the sodium or potassium ions are equal inside and outside the cell. But you can see there is another factor also coming into picture. These ions have charge also, isn't it? Sodium is positive and potassium is also positive. So there will be always a tendency for the charges to move across the cell membrane to make the concentration gradient nullify the concentration gradient, or the concentration gradient has to be zero. And also, once these ions move across these channels, these positive charge is also there now. Charge will also try to repel. When more potassium ions move across the channel and reach here, now the positive ion potassium charge will be more here outside the cell. Now, when another positive charge potassium channel tries to move across the cell, it will be repelled by the potassium ions present in the outside of the cell. So finally, an equilibrium will be established across the channel, across the cell membrane. That equilibrium will be between concentration gradient and the potential gradient, isn't it? So concentration and potential gradient will finally come to an equilibrium, and further movement of ions will not happen. That will happen once the impulse is applied to the neuron. Okay. So that is all about the movement of ions. So this one shows some figures which depicts it. So case one permanent ion. So if there is only potassium, see, this one actually replicates the cell membrane. Okay, this left side replicates the inside of the cell, and right side replicates the outside of the cell. So initially, say, if the concentration gradient of the potassium is equal on the both sides, inside and outside. If the concentration gradient is equal on both sides, then there will not be an effective movement across the membrane. In the next case, let's consider if more potassium ion is inside the cell, then definitely ions will have a tendency to move from inside to outside. When an ion moves from inside to outside, I said this potassium ion is positive. It will take a positive charge along with it, and it will move until the concentration and the electrical equilibrium and the chemical equilibrium balances or the electrochemical equilibrium is achieved. Until the electrochemical equilibrium is achieved, the ions will start moving across the cell membrane. And when one potassium ion moves from inside of the cell to outside of the cell, it will take a positive charge along with it because it is positively charged. Finally, when an equilibrium is established, the inside of the cell will more negative, outside will be more positive. And if you put an electrode to inside, electrode inside and outside, and if we measure the potential, it will show a negative potential. Why? Because the potassium ion is moving from inside to outside, taking a positive charge with it. So finally, the inside of the cell will be more negative, outside will be more positive. So the equilibrium potential for potassium ion is minus 58, and it was measured and it was verified experimentally. So potassium ion will have minus 58 millivolt equilibrium potential. So this is the equation governing for that one. So similar to that, sodium will also have its equilibrium potential. Now see, if I am having a cell with a 10 millimolar of KCl, that means equivalent K plus ions, and 1 millimolar of sodium inside the cell. This is inside. And now in the outside, we have 1 millimolar of KCl and 10 millimolar of NaCl. So generally, in the outside of the cell, concentration of sodium will be more. Inside, the concentration of potassium will be small. So when these channels are open, these ions will move across the cell membrane. Okay, when an impulse is applied, the sense means when light falls on retina, that is an impulse. These channels will be turned on. Initially, sodium ion channels will be turned on. When the sodium ion channels are turned on, sodium ions will flow from outside to inside, because outside sodium ion concentration is more, and it will start moving from outside to inside, and potassium ions will start moving from the inside to outside. So finally, an equilibrium will be established. That is an electrochemical equilibrium. Electrochemical equilibrium in the sense means the ions will move across the cell membrane because of this concentration gradient. And since these are electrically charged, finally an equilibrium will be established between these concentration and potential gradients. So since they are electrically charged, there will be a potential gradient. Since there is a concentration across this cell membrane, there will be a concentration gradient also. Finally, at some point, an electrochemical equilibrium will be established. There will not be any flow of ions across the cell membrane. And for potassium ion, the equilibrium potential is minus 58, and for sodium ion it is plus 58. Why? Because sodium ions move from outside the cell to inside, carrying a positive charge. So finally, if the channels are open, at some point, the flow of ions, sodium ions will be stopped, and at that point, if you put a voltmeter and measure the voltage across the cell membrane, we will get a value of plus 58. So I think this is also clear. It is clear, we'll move it. So this shows actually the cell membrane. Inside the cell membrane, there will be more potassium ions. So you can see K plus I have written here. And outside, there will be more sodium ions. You can see here. Sodium ions are some other anions. So these ions will move across the cell membrane by a process called diffusion. So the movement of ions across the cell membrane due to the concentration gradient is known as diffusion. And the movement of ions across the cell membrane due to the charge is known as potential gradient. So whenever an ion moves across the channel, it will carry a charge, whether it is sodium or potassium, both will carry a charge. So diffusion, due to diffusion, the concentration gradient will be try to be equal. In the sense mean, say initially there is 10 millimolar sodium, 10 millimolar potassium inside and 1 millimolar potassium outside. So if there was no charge at the end, what will happen? 5.5 potassium will be inside, 5.5 potassium will be outside. So it will become equal. But these sodium and potassium are having charges. Due to this 5.5 millimolar inside, 5.5 millimolar outside condition will not be possible. So at some point, this electrical and concentration gradient will be equal, come to a point, and an electrochemical equilibrium will be established. That's it. So you can see here. Initially, so potassium will move from inside to outside like this. That process is diffusion, and when it diffuses, more potassium will come in outside also. Now, when a potassium comes to this point, it will be repelled also due to these potassium ions. So at some point, there will not be any further flow across the cell membrane. So these are the governing equations. So the diffusion is explained by Higgs law, and Ohm's law of drift actually explains the potential gradient, actually the drift of ions. So this is Einstein constant, and at some point, as I said, there will not be further movement of ions. So J is equal to J diffusion plus J drift will be equal to 0. So at equilibrium, it will be equal to 0. And equating these equal to 0, we will get the equation for the potential across the membrane. So J diffusion and the J drift are the two governing equation, which actually says the nature of flow of ions across the cell membrane. So these are actually the signs of movement of ions across the cell membrane, which actually create the action potential. I know these may be new for the students from electrical. Okay, if you have any doubt, you can ask in between. I am ready to explain all those things. And in case of a cell membrane, these are the concentration gradients. In case of mammalian cell membrane, these are the concentration of concentration of iron. So Na plus ion concentration will be more outside. So inside the concentration will be 5 to 15 millimolar. Outside it will be 145 millimolar. Potassium inside concentration will be more, 10 times more than outside. Okay, and outside chlorine concentration will be more. 110 millimolar will be the outside concentration, 4 millimolar will be the inside concentration. And you may have one doubt, how this much difference across the cell? We have channels there, then somewhat it has to be, it has to be come to an equilibrium. The sense means we have channels and we have pumps also. Channel will allow the free flow of ions across the cell membrane. But these channels are not open always. The channel will open and close when an impulse is applied, naturally or artificially. We can also provide some impulse. Okay, so right now I am providing some impulse to you. Visual impulse is there, auditory impulse is there. So whenever there is an impulse, these ions channels will open. Whenever there is no impulse, these channels will be closed, and the potassium, these pumps will operate, and the pump will maintain this concentration gradient. Why this concentration gradient has to be maintained? Because whenever an impulse comes, some potential has to be generated. Some potential has to be generated. Some waves has to be produced. That is action potential. Whenever an impulse comes, an action potential has to be generated if the impulse has some strength, so that it will produce a threshold. Whenever that impulse comes, whenever a threshold is happening, an action potential has to be generated, isn't it? So the pump will actually maintain the potential, maintain the concentration gradient in such a way that whenever an impulse comes, an action potential will be generated. An action potential will be generated when some channels are open in sequence. In sequence, that channels has to open. When in sequence that channels are opening, then actually action potential will be generated. Okay, that is the case of a neuron. So now that I will explain which channel should be opened first, which channel will be opened next. Whenever an impulse comes in first, sodium ion channels will be opened first. So when sodium ion channels are open, what will happen? When sodium ion channels are open, sodium ions will start moving from where to where. So if you can observe this figure, it will be clear from where to where the sodium ions will move. Definitely, the sodium ion concentration is outside the cell, and inside the cell the sodium ion concentration is less. You can see 5 to 15 millimolar. Outside it is 145 millimolar. So suddenly when an impulse comes, sodium ion channels will be open. That is the mechanics of the neuron operation. Suddenly an impulse comes, sodium ions will open. So all the sodium ions which are outside will start running, and it will move through the channel and it will move inside. While doing so, what will happen? It will take a charge also, positive charge also, and ineffectively the membrane potential will move towards sodium ion equilibrium potential. The sense means when only sodium ion channels are open, the potential will move towards sodium equilibrium potential. Okay, so if only potassium ion channels are open, then the membrane potential will move towards equilibrium potential of potassium ions. Okay, so if only chlorine ion channels are open, then the equilibrium potential of the membrane will move towards chlorine equilibrium potential. Now, when impulse is applied, sodium ion channels will open initially. Then what happens actually? All the sodium ions will start moving inwards from outside of the cell to the inside of the cell, and the membrane potential will start increasing, and it will try to reach the equilibrium potential of sodium, and it will start moving from a resting potential. That resting potential is minus 70 millivolts. So whenever no impulse is applied, this ion pumps will operate, and it will maintain a potential across the cell membrane that is minus 70 millivolt. Okay, so from minus 70 millivolt, the membrane potential will now increase, and it will reach to sodium equilibrium potential, that is plus 90. Okay, now once this membrane potential starts increasing, then some other channels will also open, because these channels are actually Na plus and sodium and potassium channels are actually voltage dependent. Whenever there is some voltage change, these channels will open or close. So when the membrane potential will become more positive, potassium channels will open. And what will happen when the potassium channels open? You can see here, potassium ion concentration is more inside than outside. Inside it is 140, outside it is 5. So Now potassium channel will move from inside to outside. And when potassium channels start open, then the potential across the membrane will be moving towards that equilibrium potential of potassium, that is minus 90. So initially sodium ions opened, then it moved towards positive. When the potential increase due to the increase in the potential, sodium ion channels, potassium ion channels will open. Okay, then potassium ions will start moving from inside to outside. Then the potential will become more negative. So initially from minus 70, the potential increased to plus 90. Now the potassium channels are opened, then it will move again to negative. It will try to reach to minus negative. So you can see from minus 70 to plus 90, then again to minus. So you can see it will complete a cycle, isn't it? So whenever an impulse is applied, it is above the threshold, this will happen. A positive upgoing, then a negative downcoming. So this all process is actually constituting an action potential. So see, depending upon an impulse which is applied to say rods or cones, an action potential is generated. So definitely that information in that particular signal is now in that action potential. Okay, depending upon the intensity of the impulse, maybe light, sound, or anything, depending upon the intensity of that particular impulse, number of action potential will be generated. So in the number, or we can say the frequency of that action potential, the information of the outside world, that can be a color of flower or music or some sound signals, anything. So that will be encoded into the action potential, number of action potential, or the frequency of action potential. And now it will be propagated all the way from the optic nerve or auditory nerve for ear, optic nerve for eyes, through this nerve, through the particular center in the brain, to decode it and produce the particular image or sound or particular noise. So the center for eyes, the signal from the eyes is actually in the occipital lobe. That is known as the visual cortex. In the visual cortex, the information from the retina will be interpreted. So you can see all the neurons are going to produce same action potential, all or none. I will show that action potential later. The signal will be same. There will not be any change. But that particular center in the brain is actually going to interpret it. Okay. So do you have any doubt in this portion? Okay. So we have discussed this resting membrane potential. So whenever the a neuron is resting, the potential across that neuron is known as resting membrane potential. That is minus 70. Whenever an impulse is applied, some changes will happen. Some ion channels will be open, some will be closed. Sodium and potassium, what we have already discussed. Then there will be some potential that is known as receptor potential. Whenever the receptor potential is beyond that threshold, an action potential will be generated. Action potential actually carries the information of the outside world, and that will be propagated to the brain, and the brain will interpret that action potential and produce the useful information. And one thing also I would like to pass through your information. Actually, I may take some more time, sorry, because I am going a bit slowly. How the brain produces the subjective experiences is not yet known. In the sense means the taste in that particular stuff, when you are eating something, how that taste is interpreted by the brain, because that taste or sound or smell, everything is propagated in the form of an action potential. Okay, if the taste have more intensity, more action potential will be there. And these signals, these electrical signals, these electrical potential will be carried all the way through the neuron, which is equivalent to wires. And the brain will produce some subjective experience. Subjective experiences of seeing a color, greenness of the green, redness of the red. Okay, all these will be produced by the brain. These are called the subjective experiences, and we call it as conscious experiences. How these conscious subjective experiences are produced in the brain is not known. It is a mystery, and the scientists are trying to find out. And this is actually known as the hard problem of consciousness. Hard problem of consciousness means how subjective experiences are produced inside the brain, because the signals are electrical, and all the signals, all these impulse are producing same kind of signals, and some part of the brain are dedicated to this particular kind of impulse coming from the outside world. And one more interesting thing is that this particular occipital lobe, where the visual cortex is there, where the visual information or the visual action potentials are interpreted and useful images, colors, or all the stuff are created, can be used for interpreting the auditory signals also. The sense means you may have also heard those who are blind will be more efficient in interpreting this sound signal, because there is a phenomenon called brain plasticity, or simply plasticity, by which some part of the brain which will be dedicated to some other function will be gradually, if it is not used, will be modulated and used for some other purpose. In the sense means the occipital cortex, where the information from the retina are interpreted, will be used for this interpreting the auditory signal if for a prolonged time signal from eyes are not there. So in the sense means the area of the brain which is decoding the information from eyes will after some time decode the information from other parts of the brain also. How it happens is not at known, but the brain is plastic. So it is having a plastic nature also. So in the sense means what I was trying to say, that if that is why we always say, if you have an intensity to do something, in the sense means alchemist, in the alchemist it says now, so you can do whatever you like to do. In the sense means you can train yourself and change the complete pattern of your brain wiring. In the sense means a bit of psychology also I will go through now. The sense means from the childhood also always onwards our brain will be wired depending upon the inputs that we are getting from the outside world. All the inputs, all the information that we are getting from the outside world, the brain will be wired in certain way, and after certain time we will be addicted to that particular pattern which has been founded in our brain. So, and one thing is that we can even completely change our brain wiring. Once we decide to change our wiring, it will gradually change. The sense means why I was pointing out is because definitely during our childhood, all the inputs that came from outside world, maybe some kind of traumatic also, some kind of trauma inputs may also come. In the sense means all the inputs may not be positive. Some negative inputs may also come that may traumatize somebody. Okay. And these traumas may get accumulated in the brain, because in the sense means when new inputs comes into our brain, the neurons will fire, and the neurons will fire and all neurons that are firing will connect each other. The neurons will fire, will connect together, and some patterns will be formed. And in the sense means if it is a pain input, a traumatic input, and some neurons will be fired, and it will form some patterns in the brain. And if those kind of pain inputs are predominant, if it continuously comes in, these wiring which has formed will become hardwired. The sense means when that signal comes again and again and again, then that pattern will be predominant, that will stay long. And this is actually the unconscious wiring. So this, in the sense means mind is related to this wiring, and that wiring will be there, and actually that will be affecting our daily life also. And the whole process of understanding what is within us, in the sense means what kind of wiring that I have gone through, is actually what is meditation. Meditation is observing oneself and understanding oneself. So I will take another 4 or 5 minutes to explain this mind part also, which is related to this. And this mind and brain, how it is connected, is also one important question in this particular stuff. And the mind, what we generally talk, the conscious and unconscious part is basically brain centered. So brain produces that mind. So we are not going deep into the other realms of the mind now, because we, in this particular talk, we are only interested in conscious and unconscious part of the mind, and how we can model it electrically, and how we can interpret it. And this conscious and unconscious mind part is actually centered in the brain itself. And this unconscious part of the mind is generally not known to us. But this unconscious part of the mind influences our day-to-day life also. And in order to understand this unconscious part of us, that actually has a very important role in our life. Because once, if you doesn't know the unconscious part of us, it will affect our daily life, basically. That unconscious part of our mind basically may contain a lot of pain related information also, trauma also, because we all definitely go through many traumatic incidents from childhood. Different people may have different type of traumatic incidents. These all will be embedded in the unconscious part of the mind. So the whole process of meditation is actually observing oneself, and we generally say it as introspection, self-observation, like that, and understanding the unconscious part of the mind. Yet now we are not able to model it completely. I said the subjective experience of the human beings are not completely modeled. It is the hard part of the consciousness. So by observing oneself, but we can go deep into different realms of our mind and understand what is hidden in the unconscious part of the mind. So if it is more trauma creating, you can understand yourself and you can go beyond the trauma. But if you cannot understand it, it will be there deep inside the brain. You may not know what all are there deep inside my mind, but it will affect your day-to-day life. So once you can observe yourself and go deep into yourself, you will understand more what is there within my mind, which I even doesn't know. Then you can go beyond it and you can rewire your brain, and then you can use your brain more potentially. So actually, if you can use our brain, some part of the brain more usefully, then it will be very useful. If not, if it doesn't go deep into oneself and understand more what is hidden within ourselves, then this will affect our activity of the brain, and it will be limited to some traumatic, unknown, hidden part of this unconscious brain. And as I said, in case of a blind person, the visual cortex will gradually aid other senses. That is why those who are blind, those who are cannot hear, will have other senses more accurate, because the brain nerves or that particular portion was used for other sense will be dedicated to the extra sense. That is why they become more active on other sense. And also they will concentrate their brain part. Their attention will be dedicated to that particular sense. So the brain, due to its property of elasticity or plasticity, will help for that. So what I was trying to say about, if we guys go deep into ourselves and deal with what is unconscious within ourselves, then that part which is dedicated to that brain part or nerves, neurons which are wired and holding that unconscious memory, which is pain, which according to the language of Eckhart Tolle, is the pain body, will be dedicated to some other purpose. That will be very useful. Okay, and I am going back again to action potential and all that stuff. So this is the action potential. From minus 70, it will move to positive, then it will go back to the negative. So you can see here, sodium channels will be open here. Here the potassium channel will be open. Then you can see this is the action potential. This is the only electrical activity actually happening in the brain. So simple. And if the intensity of the impulse is more action potential will be generated. Now, the thing is that within the brain, there are large number of neurons. These all are connected together. Okay, these all are connected together and these all fire together and potential will flow across here and there. So see, I said 86 billion of neurons are there. So I hear, I see, all that kind of. So 1 minute, one question is there. I will go through that question and I will come back to this again. What do you mean the pump maintenance? It is by Jitendra. Hello, sir. Sorry to interrupt. It's okay. No issue. What did you mean the pump maintains the inside and outside chemical unequilibrium so that every time an impulse comes, which in turn brings the both sides to equilibrium? Will it be reversed? It's a good question. Actually, the pump actually maintains the concentration gradient across the cell membrane. In the sense, if there is no pump, there will not be any concentration gradient across the membrane. If there is no concentration gradient across the membrane, if an impulse comes, when an impulse comes, the ions will not be open and closed, but there will not be any flow of ions across the channel. So the nature has been intelligently created such a cell so that there is a pump, there are channels. So pump will maintain concentration gradient so that when an impulse comes, channels will open and close, ions will flow across the channel. If there is no concentration gradient, there will not be movement of the ions. We need to have some movement of the ion so that information of the impulse can be encoded into this action potential. Actually, the number of action potential is going to encode the information of the outside world. Okay, if there is no ion channel, there is no pump, this encoding cannot happen. So there is an intelligent design of the nature in this way. So that's why actually we may think why there is a pump. So that is why that kind of an intelligence acted in this particular membrane so that there are pumps, there are channels. And in this particular part of this cell membrane, sodium and potassium ion channels are predominant. I said there are calcium ions, there is chlorine ions, and why there is no channels here. Calcium ion channels are actually more in the synapse, where two neurons are coming and meeting together. Their calcium ion channels are there. Actually, that is not there in this particular topic of our discussion. That is why I'm not going to that portion. Actually, for modeling and for decoding that brainwaves, that is not needed. That is why I'm not going. But someday, if there is another talk, we will definitely go through that also. Synaptic transmission also. That is why I didn't include potassium ion channels here. And actually, Jitendra, is your doubt over? Actually, potassium ion, actually the pumps actually maintains chemical unequilibrium, chemical concentration gradients across the membrane. Okay. So I move to the next slide now. So the number of action potential actually have the information. The action potential is actually all or none phenomena. This will be always in this shape. The shape won't change actually. So two scientists named Hadgin and Hawksley observed this cell membrane and they came up with a model. And Hadgin was a physiologist and Hawksley was a biophysicist. They observed this iron, what is the cell membrane, and they came up with a model. It is known as HH model or Hadgin-Hawksley model. And they won a Nobel Prize in Physiology or Medicine in 1963. So that mathematical model is actually an electrical model. And I will go again back to the, I will show that model, but I wish to ask to you, can you just predict the model from this stuff? Simply, that is a very simple model. Actually, not only for predicting the model, but also they perform the experiments. And we are not going to discuss that experiments here now because that is a full big book. There is no time. And I will share the book title here. And somebody who is interested, I will share the PDF also. And later, if you needed, we will discuss that working also of that model. But now I am interested in asking, can you just predict? Because it is a very simple model. For an electrical engineer rating, it is cup and cake. So from here, I will give you some hints. You can also think, I will show positive and negative plates. Here it is positive, here it is negative, separated by insulator. That is one stuff which is there in the cell membrane. This is cell membrane. Cell membrane have positive and negative electrode, and insulator is there. It separates these two. And there is ion channel through which ions move across. So there is a conductor. Ion channel is a conductor. Through conductors, electrons moves now. So through ion channels, ions are moving. So that this one is equivalent to some stuff in electrical network. So how we represent a conductor through electrons is flowing. How we represent a current carrying conductor. Some symbol we use generally. Can you say what it is? Somebody who is ready to respond. It's an interesting stuff. Actually, the model Hadgin and Hawksley made is a very simple model, and that this is a model. So a positive and negative plate separated by insulator is a capacitor. And a current carrying conductor is nothing but a resistor. So this is a resistor. So here comes the resistor, here comes the capacitor. This actually denote the membrane potential because there is a potential across this membrane now. That is denoted by this potential. So this is the equivalent of a cell membrane. This actually got a Nobel Prize. So actually they predicted this model and they performed the experiment. Different experiments they performed with about ion channels. They blocked one ion channel and they predicted how the cell is going to behave, and it behaved the exact same way. They blocked another ion channel using some ion blockers. Okay. So this is actually the equivalent circuit. So do you have any doubts? If you have any doubt, you can ask. So yeah, very good. Actually, Jitendra was responding as capacitor. That was capacitor. Very good. Actually, this another stuff is a resistor. So this is the model. This is the model that they developed. So that means if you can look into different structures or different stuff in the nature, deeply we can understand something which is hidden in it. So within these neurons, actually, there was some capacitor, resistor, and batteries, and it was able to model a neuron like this. And now we'll go to the next slide. So this is a detailed circuit of a neuron, because I said there are potassium channel, sodium channel, chlorine channel, and a calcium channel. So there will be all these channels will having conductance. Sodium channel will have sodium conductance, this have calcium conductance, this have potassium conductance, this chlorine will have chlorine conductance, and the capacitance will be one only, because number of capacitance are connected parallelly. That will all add up together, and there will be one capacitor only. And this is sodium equilibrium potential, this is potassium equilibrium potential, this is sodium, this is calcium, this is potassium, this is chlorine equilibrium potential. In the sense means, if there is only sodium ion channels and sodium ions, when the channels are open, the potential will be moved toward sodium equilibrium potential. That means these all are removed, then the potential will be, when the channels are open, this will be maximum. Then ENA will be the potential, like that. So that is all. So we can write the potential and the current IM is equal to d dV by dt is the current through the what to say capacitor. INA is this current, IC is this current, IK is current through potassium conductance, and IC is the current through chlorine conductance, simple electric system. And GNA is the conductance, reciprocal of resistance. So GNA into V minus ENA. V is the potential across this, ENA is the sodium equilibrium potential. So that is actually the model of the neuron. As if you have any doubts on this portion, you can ask and we'll discuss. So the modeling part is over, and most of the experiments were conducted on a skid axon. Why he conducted on a skid axon? Because he cannot conduct it in humans. There is no permission to conduct invasive experiments in humans. And there is another reason he precisely chosen a giant axon, because these giant axons are very large. Mammalian axon is having only 20 micrometer diameter. So this inside stuff. Skid axon have 1000 micrometer. So we can insert an electrode inside. We have to insert an electrode inside, and we have to place an electrode outside and measure the potential difference. Then only we can understand the working. So the skid axon have potassium and sodium, chlorine, everything inside and outside. The concentration gradients are different. Concentration of these ions are different, but the nature of this potential, the concentration in the sense means nature of the distribution is similar. So for referring for this particular section, you can use this particular textbook. So those who are interested can also mail me or also call me. I will give the PDF. And this book have the model and the different analysis Harding and Horsey have carried out to prove their model. Okay. Now we'll come to the next portion that we'll finish quickly. So why we need to interpret the brain wave? Because we cannot put electrodes inside the human brain, which is a human neuron which is within the brain. We cannot do that. So if we can insert electrode to particular neuron, say, which is in a cerebral cortex or which is in hippocampus, if you can insert an electrode there, then you can precisely say how much potential is there, then we can interpret data from that particular signal, isn't it? Generally, what we do, if we can get a particular electrical signal, how we'll go about that signal? And actually, I think some of you have studied signals and systems. Signals are signals. In the signal and systems, we do this FFT, isn't it? Fast Fourier transform, all the stuff. By doing all this signal analysis, we can interpret what kind of data is within that particular electrical signal. So if you can insert an electrode to a particular neuron in the hippocampus or a cortex or any other place, we can measure the electrical activity and we can actually interpret the data. But in case of human being, we cannot do that because we cannot insert electrode directly to that particular portion. So what we can do is that we can use some methods which is not that invasive, and we can measure. So there are different methods. fMRI is there, PET is there. Okay, and generally EEG is used to measure the electrical activity. fMRI actually measures the metabolic activity of the brain. Okay, so we use some kind of chemicals, and that chemical will be injected, and the radiations produced by the chemicals will be used to predict the activity of the brain. But EEG precisely measure the electrical activity of the brain. But there is another issue coming here. We are not going to, you are not only listening to me now. You are looking to the slides. So visual stimulus are there. Auditory stimulus are there. Now you are feeling the world, isn't it? The hotness, the coldness, everything you are, all kind of signals are randomly coming inside the brain. So the brain activity will actually, the EEG measuring activity will have all these signals mixed together. Okay. So the electrodes that we are placing outside the brain will actually tap all these. So it will not be an action potential. If you place electrodes in the neuron, you will get an action potential. But outside the brain, we will place electrodes here, everywhere. Okay, number of electrons will be placed, and these electrodes will catch the electrical activity. That will not be actually the action potential. It will be sum of all these activities happening inside the brain. So that stuff is actually called the brain wave, and different kinds of brain waves are there. And these brain waves are classified based on the frequency, amplitude, and the shape. And the brain waves actually are called as alpha, beta, gamma, delta, mu waveforms. And these waveforms actually differ during different activities. When I close my eyes, actually there is no input signals through the eyes, but the occipital lobe will produce alpha waves. That alpha waves indicates this part of the brain is now inactive, not processing any information. That is indication that says the eyes is closed. So when I'm getting an information or a brain wave from occipital lobe, occipital cortex, and if it is alpha, then from that waveform I can say my eyes is closed. So that way we can interpret. So in the sense means I doesn't need to collect the information from occipital lobe and say your eyes are closed. That is not the purpose. I was just given an example. So what is Indian is that if there is some brain disorder, say epilepsy, schizophrenia, any kind of apnea, any kind of brain disorder, if you are getting the brain wave, we can collect the brain wave. By analyzing the wave, we can predict which part of the brain is malfunctioning. Okay, that is one purpose of collecting the brain wave and interpreting that. It is not only that one. We need to know much about brain and mind also, isn't it? Everybody is interested in knowing about the world, about the universe, all those stuff. So we need to interpret the data in that way also. So this is actually the history of the development in brainwave interpretation that you can just go through it. So this we have discussed. So Hans Berger actually developed this EEG technique. And you can see here the electrodes will be, these are the electrodes. This will be connected. and you can see using this stuff, we will put some gel also. That gel will be applied to the head so that the resistance will be minimum, because we'll have hair also in the head. So the electrodes has to be placed deeply into the brain, and some gel has to be applied to reduce the resistance. So these are the electrodes. Through this we will apply the gel. So like this finally comes. So we doesn't need to remove all the hair, but I took this on this picture because this actually depicts that electrode placing much more similar. So you can see electrodes will be placed like this, and these electrodes will pick up the electrical activity. So this is actually an EEG. So see, this is not actually an action potential. This is an EEG. So this is actually coming from different channels, isn't it? See, there are number of channels here. So these channels will give number of one activity. So you can see number of waveforms will be here. These all waveforms will have some information between. So there will be alpha waveform, there will be beta waveform. So now we'll see how we can interpret this waveform. So this particular stuff, this particular EEG waveform will have beta wave, alpha wave, theta wave, delta wave, and some other spike. When I am moving the eye, that will also pick it up. Okay, so excuse me, one more message. Okay. It's over. Within 10 minutes, it will be over. Sorry for me. So beta wave will be 13 to 30 hertz. Alpha will be 8 to 13 hertz. Theta will be 4 to 8 hertz. Delta will be 0.5 to 4 hertz. So like that, the waveforms will be of different frequency. So by interpreting this particular frequency, we can understand which the activity of that particular brain region. So alpha wave is like this. It is from 8 to 13 hertz. It is of low amplitude. It indicates that particular part of brain is relaxing. Now it is not taking any input. And this waveform will be, theta waveform will be around 4 to 7 hertz. It will be prominent when you are drowsy and when you are stressful. Delta is around 3.5 hertz. It occurs during deep sleep. New waveforms will be in this shape associated with physical movements. And whenever there is some malfunctioning brain disorders, the brain waveforms will be different. All the reference for this will be available in this particular book. Okay, you can actually refer this one. If any doubts, you can also ask me. So thank you for listening me, and thank you for IEEE Malabar section and MEA College of Engineering for giving me this opportunity. Okay, thank you. So you can just contact through this number. And if you have any question, you can ask me. Thank you.
Thank you, sir. Thanks a lot. So if you have any questions, you can ask now. You can type it in the chat box or you can ask by voice. Hello?
Hello. Shall I ask a question?
Yes, you can.
Yes, I'm Sabrina from TKM College. My question is, now so many are doing research work in EEG data. So suppose depending upon the application, the features selected from EEG may change. But the thing, what the people are doing is they will select a common data set and then apply to different deep learning or machine learning algorithms and do some processing. So suppose for a particular application like emotion detection, or if it is for classification of alcoholic and non-alcoholic patients. So which type of or which feature we have to take for consideration? You are in mute, sir.
Madam, if you are going to study some kind of emotional studies, first of all, we have to set some cues, some experiments, which actually will activate the brain regions, which are more emotionally oriented. In the sense means the particular type of experiments researchers generally will set is they will try to show some images, which will activate our emotional response. In the sense means when I am showing you picture of an ice cream, that will create a particular kind of emotion. If I am showing another image of an accident, then it will create another type of emotion in you. So like that, we have to set the experiments. That kind of experiments has to be first set up. Using that experiment, you have to take the EEG readings. If we are not setting up any experiments, then we cannot say that these type of EEG readings are an indication of emotion, because EEG, when you are giving some emotional images, then that emotional images will produce some action potential and it will be processed into the brain. In the sense means that particular information will be encoded and the emotional senses will be activated, especially the amalgama. Amalgama region is actually for more this fight and fear and all those stuff. Then only we can say this particular EEG reading is corresponding to that. That reading we can use for doing experiment. Generally EEG, if I am sitting here and if somebody comes and take my EEG, that I can only say that is wake EEG. I am wake, this EEG for a wake person, and I can do analysis for wake EEG only. That EEG we cannot use for any other purpose. Is it clear, ma'am, or any clarification?
Okay, sir. So, according to the situation or according to the patient, we have to collect for what purpose we are selecting the ECG. We have to collect the corresponding data. So my doubt is in that particular set of data, whether we have to select the theta wave or that particular thing I am asking. Suppose you are getting.
No, actually, when you are collecting the EEG wave from the brain, definitely theta, beta, gamma, all these waveforms will be there. We doesn't need to particularly collect a particular type of waveform. For an example, I will give an example. I'm going to find out, I'm going to do an example, an experiment where I'm going to study whether heart beat or the heart activity is influencing the brain. So I will put an electrode here in the head region, that is the ECG, and I will put electrodes in the brain. So the electrodes in the brain will give EEG, and the electrode in the heart will give ECG. Now I am going to study whether the ECG or the brain or the heart activity is influencing the brain. So whenever the heart activity is influencing the brain, the alpha power will be low. Okay, the brain wave will have all these waveforms. Alpha will be there, beta will be there, gamma will be there, and mu will be there. All the waveforms will be there. I have to plot the FFT of that particular activity in the brain. From the FFT, I have to point out where alpha is there or not. Alpha is from 8 to 12. Isn't the frequency of alpha is 8 to 12. So the FFT will give the power of each frequency in that particular brain signal. So if there is more alpha means 8 to 12 region will have more power in the FFT. So by analyzing that one, I can come to a conclusion that alpha is more or alpha is less. If alpha is less means that particular brain part is active. In the sense means the logic is that when the alpha is more, that particular brain part is not active. When I close the eyes, occipital cortex will show more alpha waves. Okay, so when I am going to a study how heart rate is influencing different parts of brain, if the heart rate is influencing this part of the brain, then alpha will be less. That is logic. And all these waveforms will, all these frequency will be available in the brain EEG, which is our interest. That we need to take them, take from that frequency plot, FFT.
Okay, sir. Thank
So
you.
if it, okay, if our need is alpha, from the FFT we have to choose alpha, and beta is in another frequency range. All these frequency range you will get from the FFT, and we can analyze all the processing of this EEG waveform. We need signal processing. That what we have studied in electrical engineering. Processing is filtering. Filtering need signal processing knowledge. Convolution, that what we have studied, the convolution is needed. Those kind of activities we have to do on this particular signal to extract the information. Is it okay, ma'am? Thank you. Thank you for listening.
So is there anybody to ask questions? So I think the questions are over. Sir, is there anything else you want to cover up of the wrap up?
No, it's complete.
Okay, thank you, sir. Thanks a lot. We have come of an end to our webinar. Now, first, I would like to thank on behalf of the IEEE Malabar Subsection and IEEE Malabar Hub and IEEE MASB, the speaker of the day, Dr. Dileep, sir. It was a wonderful and interesting section, very informative. Next, I would like to thank Mr. Sabik PV, Chairman of IEEE Malabar Subsection. And
Adu Satyano, actually Satyano.
Satya, sir.
Okay.
Really interesting.
Okay. So I will check my
Interesting.
mail and I will wait for some calls also. If something is interesting, then somebody will definitely contact or somebody will ask for the
Sure, sir. It was a
clarification.
interesting section. Yes. This type of topics are new to us and very interesting to hear. Okay, thank you, sir. Thank you very much for such a wonderful section. At last but not the least, I would like to thank all the participants for the lively participation. We appreciate you all for your being here. Thanks again for joining today, and we will see you the next time. So all of you, please don't forget to fill the Google form. Okay, thank you, sir.
Okay, welcome. Have a nice day to all. Good night.
Thank you, Dileep, sir. Thank you, Dileep, sir, on behalf of IEEE Malabar Subsection. Thank you.
Okay, bye.
Okay. Welcome.